section. 15? Sure. Find 15. And let's... Okay. What's a positive square root function look like? We should all be able to draw a positive square root function really quickly somewhere on a piece of paper. Positive square root of x without graphing it on a calculator, because you should know what a positive square root looks like. Do we not know what a positive square root looks like? I'll demonstrate. It looks like that. Top half of the sideways opening parabola. Now this one's a little bit unusual, right? Because 4 minus x is not, you're used to seeing things like x minus 4. Well, 4 minus x, by doing that little trick, ends up reversing the direction of it, sending it not to the right, but to the left. Okay? But we got some other stuff going on here. We got an x plus 1 in the denominator. What does that x plus 1 do for your function? What do you know when you see that x plus 1 in the denominator? Okay, that's not a movement. In the denominator, when you see a factor, something, it does not hit that spot, right? Sounds like a vertical asymptote, right? We know that vertical asymptotes come from those factors in the denominator. Non-removable factors, that is. Now, it would still be a discontinuity if it was removable. What kind of discontinuity would it be called? If you could remove the factor, which we can't, what kind of discontinuity would it be called? Removable, right? That's how we get that concept of removable, is because we can remove the factor, but that doesn't happen here. So that x plus 1 is causing a vertical asymptote. What about this x squared plus 1? Well, folks, that's a sum of squares, and the only way you can factor that is if you have imaginary numbers. So that's not contributing to any kind of vertical asymptotes. You're definitely going to have a calculator to graph this thing, because it's not going to be something normal. So y equals, clear, clear. And we'll do the alpha y equals, so I can get that little fraction thing going. And maybe I should put this up on my camera. Should probably type that first. 4 minus x. Oops, that isn't what I want. Bring my camera back up. Faster. All right, so we got our function entered in. For those of you that have an old style calculator, you'll probably need a set of parentheses around that entire denominator. Around the entire denominator. And for kicks and giggles, you could throw one in around the entire numerator, although I don't really think you need one because the radical probably takes care of that. So, whenever you're starting fresh on a graph, you might want to do zoom 6 just to kind of reorient the window and take a look at the picture. Do you guys see the vertical asymptote? At x equals what? -1, right? Here, let's snip this and take a look at that picture. So, yeah, we got that x equals -1 right there. Do you know any part of the domain so far? Like, could you at least give me the domain part of that piece over there on the left side? What would that be? -infinity to -1, parenthesis, parenthesis, right? So we're just doing domain. That's all we're doing here. But there's another piece to it, so obviously we're going to have a union there. And we skip over the asymptote and go to the other side, right? -1, comma. What's going on the other side? All right, now, something's going on right there. It looks a little unusual, doesn't it? All right, so let me jump back to my camera, see if we can figure out what's going on here. If I hit the trace button and I'm kind of following the graph, following the graph, following the graph. What happened? The y values just like disappeared. I had a y value right about in here, and then no more y value. Well, the unusual part about this is at 4, 0 is the last known point on this graph. That's kind of bizarre, right? That's not normal. This thing just stops. So, what are you going to say for the conclusion of that domain? What do you think?
4 bracket.
4 bracket, thank you very much. You had to include the 4 because it was a stopping point. Good. Okay. Now what? All right, I'll start asking. How about 19? Find the range of that function. What do we know we have to do? Every time I'm asking you about domain, range, any of this stuff, what's the first thing you're going to do? You're going to graph it, aren't you? Because we don't know what the heck that thing looks like. So make that fraction. Now, what's this question asking about, number 19? It's about the range. Okay? Before we go any further, maybe I should snip this and see if we can analyze what we're dealing with here. So we've got y equals x squared over 1 minus x squared. Hopefully you know that you can factor that denominator. What would you factor that denominator into? Come on, use your Algebra 2 skills. It's a difference of perfect squares, isn't it? How are you going to get two numbers that multiply together to give you 1? How about 1? Nice job. Okay, now, how about x squared? See, you guys are used to doing things like this, x squared minus 9, and you go x plus 3 and x minus 3, right? You guys would do that in a heartbeat? That would be easy for you. Now I've reversed it. So, 1 minus x squared, so that would be 1 minus x and 1 plus x. Okay? What are these two things in the denominator telling you? What? Those are the vertical asymptotes, right? So we got a vertical asymptote at x equals 1 and at x equals negative 1, right? These are my vertical asymptotes. Which makes sense. You can see those in the picture. Do we have any horizontal asymptotes? Oh, that's what we talked about yesterday. Right? We want to know the limit as x approaches infinity of x squared over 1 minus x squared. And we can do the negative infinity as well. But I think this will kind of get us the picture. And what did we talk about doing yesterday? We did it several times with these rational functions. Something to do with something in the top and something in the bottom. What were we looking for? Hopefully you wrote it down somewhere. The largest power of x in the top and the largest power of x in the bottom. And what are you supposed to do with that fraction? Supposed to reduce it, right? So what does x squared over negative x squared reduce to? Negative 1. So what's the limit as x goes to infinity of negative 1? I'll list out some of the terms for you. Negative 1, 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 negative 1. What do you think it's getting closer and closer and closer to? Negative 1. Nice job. What's the horizontal asymptote? Horizontal asymptotes are horizontal lines, right? How do we write the equation of a horizontal line? I'll start you out. Y equals negative 1. Thank you very much. Nice. Right? So we've got a horizontal asymptote at y equals negative 1 and vertical asymptotes at x equals 1 and x equals negative 1. Now hopefully you can look at that picture and see all that information. Because now I'm going to ask you for the range. And to help you understand the range, I'm going to turn the graph on its side. Okay, so on this particular picture, where is negative infinity for the y values? Wouldn't that be over here? Those are negative infinity for the y values. And where would positive infinity be? Of course, it'd be over there, right? So help me find the range. Negative infinity to what? Okay, now why did you stop at negative 1? Why didn't you go all the way to 0? Because of that horizontal asymptote. If you didn't pay attention to that horizontal asymptote, you'd be crossing it accidentally. All right? Somebody other than Mr. Fields. What are we thinking about for the next part? Yes? All right, so when we say 0, comma, infinity, I know we got a parenthesis there. What do we got on the other side? Good job. I'm impressed. You must include the 0 because it is... That part in the middle does hit the origin. You're right. Nicely done. All right, what else? Oops. Yep, got one. 29. Ooh, yeah, one of these. Why isn't it moving up? Oh, I see why. I see why. Okay, so I'm going to have to graph this. For those of you who do not know how to graph absolute value functions, let me show you. So I come up to my y equals, and I hit the math button on the left side. On the left side, the math button is real close to the alpha button. And then I see the NUM across the top. And what's the first one in the list? Anti-lock brake system. Okay, well, she coughed over that joke. All right, never mind. So we had x plus what? 29? X plus 2 and a minus 1. Oops, not 2, minus 1. All right. What do we want to know here? Intervals on which the function is increasing, decreasing, or constant. All right, looks like we got an increasing and a decreasing. It does not look like we have anything constant. So, what about this section over here? What's this part? It is decreasing. Remember, we move through the graph from left to right. It's just like a roller coaster. It looks like we're coming downhill. So that would be a decreasing, and what would that be? Negative infinity to negative 2. Don't include the point negative 2 on either one of these intervals because it's not increasing or decreasing. It's just a dot right at the end. So it cannot be considered one or the other. So what's the other section? How about negative 2 to infinity? I'm not too concerned about these kind of graphs. I am more concerned about these kind of graphs. When you're doing a function and it looks like something like this, like a parabola, and it's upside down, we're asking increasing, decreasing, and I get something like this. So we're increasing from negative infinity to, let's just say that was negative 1. Okay? And then they're decreasing from negative 1 to negative infinity. Tell me what's wrong with this picture. Okay, I'll put a line through here so you know it's a completely separate problem. I saw this happen today, right? Okay, yep.
It can't be negative infinity on the right side.
Okay, all right. Can't be negative infinity on the right side. Okay, number one, this is smaller than this. That's a problem. We always write our intervals smallest on the left, largest on the right. Can you describe to me what's going on in this kid's mind?
They're thinking that down means negative, but it's left is negative.
See, in their mind, what they're seeing is, I want to say from here this way, but in their mind, they started with an x value, and suddenly their mind went y value. And they wrote negative infinity because in their mind, they see it going down. Remember that you're splitting up the axis based on x intervals. The word increasing or decreasing is describing what's going on with the y's. Yes. Sure. So, yeah, just put a positive infinity on that kind of thing, and that takes care of that one. All right. Got another one? Yes.
31.
39? Okay. So, question 39, I believe that's the half circle one. You're dealing with, if you graph that on your calculator, I'm pretty sure you're going to get something that looks like this. Is that right? Okay. Getting all kinds of questions about this bounded above, bounded below, or the term bounded. Can you draw a line on this graph anywhere? Any horizontal line. Has to be a horizontal line, I should say. And the graph will never go above it. Can you draw any horizontal line and the graph will never go above it? Sure, there's lots of them. So we can say that this is bounded above, right? Can you draw any line that it won't go below? Sure, we could even use the x-axis, right? Bounded below. By the way, this other line could come and touch right there at the top. Nothing wrong with that either. If you have both of them, what do you have to say is the final answer? That this is bounded. If you've got bounded above and bounded below, then the overall answer has to be that the graph is bounded. So get that in your mind. Can I draw a line above that it won't cross, that it won't go over? Can I draw a line below that it won't go below? And if I can do both of those, then it is bounded. Yes, you need to see a picture. Yes, you need to look at those pictures. How about question 22? Oh, I know what you're thinking. You're thinking, well, Mr. Staley, you didn't ask us to do number 22. That's not an odd one. Okay, that means everybody in the room has to do it right now. Okay, come on. Question 22. Graph the function and tell whether it has a point of discontinuity at x equals 0. If there is a discontinuity, tell whether it's removable or non-removable. Okay, so question 22. Do you think there's a point of discontinuity at x equals 0? Just look at the function. I don't have to look at the graphing calculator to answer that question. What are you looking for? Where in this fraction are you paying the most attention to figure out points of discontinuity? The denominator. Okay, so what happens with that thing, x? What's the only number in the universe that you could plug in for x which would cause the denominator to end up being 0? 0 itself. So we do have a point of discontinuity at x equals 0. The question is, what kind is it? Can you factor the numerator? Can you factor the numerator? Is there anything that you can do to that numerator? May I suggest a GCF? Can you pull anything out? You can pull an x out, right? If you do that, what are you left with in the numerator? X squared plus 1, right? And what do you notice? Those cancel, right? What situation is that creating? If you can remove the factor, what kind of situation is that creating? A removable discontinuity is appearing. I didn't even graph this thing, and I know that's going to happen. What's x squared plus 1 look like? It's a parabola, right? It's been shifted which way? Up 1 unit. All right, so we'll exaggerate this. What should I be doing right there at 0, 1? What should I be doing at 0, 1? Okay, I'll remind you. Remember all that stuff with delta math? Removable discontinuities? There's a space, there's an open circle. Now, if some of you with the newer style calculators, especially the ones that graph in color, look at the graph. You might actually see that space show up. Now, it won't be a little open circle like I've drawn, but I've noticed on the newer style graphing calculators with the removable discontinuities, it actually puts a little space in there. You won't see that on the older style ones. Yes, it is. I need to get it adjusted so that it doesn't close so hard. I would have to agree with you on that one. Look for those kind of things to occur. I understand some of these were already factored, but some of them are not, and you need to be able to do that. Somebody else asked me about another one. Let's see if I can find it. 51. State whether the function is odd, even, or neither. Oh yeah, this was a good one. Graph it, 51. Use that graphing calculator and graph it. If you are only being asked to state whether it is odd, even, or neither, then yes, you can use the symmetry of the graph. You know, and I know that I'm going to ask you for a proof. So we're going to do both. But it never hurts. Let's see here. Negative x squared. Negative x squared plus 0.03x. Plus 5. Why is that still on there? What are you thinking? Just look at the picture, tell me what you think. Even, odd, or neither? Any ideas out there in TV land? I got to vote for even. Do you agree or disagree? Okay. It sure does look like it has symmetry with respect to the y-axis. Let's do a proof. Step 1. What is the opposite? I guess I'm just going to call it f of x. What is the opposite of f of x? Well, wouldn't that be positive x squared minus 0.03x minus 5? If I multiply what the original one was by negative 1. Step 2, plug in negative x. Go back to the original function and plug in negative x. Everywhere you see an x in the original one, you plug in a negative x. I think I did that right. Let me look at 51, make sure I did. Yep, the opposite of negative x squared plus 0.03. Yeah. Okay. So we have the opposite of negative x times negative x. Okay, so how much is this thing here in the middle? That's negative 0.03x, right? How many of those minus signs are going to cancel out on the first term? What? So on this first one, how many of the negatives cancel out? You got 3 of them, right? You got negative 1 times negative x times negative x. How many of those negatives are canceling out? 2, right? 1 pair. All right, because they always cancel out in pairs. So if I simplify that term at the front, what do I get? Negative x squared. Did we get the original? Remember the original one was negative x squared plus 0.03x plus 5. Did we get the original? We did not get the original one. Pay attention to those signs very carefully. It does not match. Did we get the same as the opposite? No, it did not match. See, if you look at that picture, you're going to bite on even. And then we got you. Now, what could you have done on your graph? Hit the trace button. Yes.
Could you go back?
Yes, I can go back to the proof.
Where did the on number 2 you add a negative in front of x squared, or now negative
Okay.
x squared?
So the original one, I wrote that down here at the bottom. Okay, so this negative right here is original to the original function. So I went through and I replaced every one of these x's with negative x. That's step 2 in the process. So that one's an original negative to the problem.
Oh,
This one was inserted along with this one.
yes, sir.
Okay, does that make sense? That's why it's extremely important to go back to the original function. Good question. So we hit the trace button. We type a 1. What do we get when we type a 1? What'd you get when you typed a 1, put a 1 in? 4.03. How could I use that to check? Remember we said opposite x's, same y's, opposite x's, opposite y's. Yes, sir. Put in negative 1. I get 3.97. That's not the same, and that's not opposite. You could look at a table. I like that idea too. We could do table setup, start at 0, or we could just do the ask and auto feature. Ask for independent variable, dependent variable auto, Go to the table. Here, I'll get rid of some of these values since they type of 1, type of -1, boom, boom, 4.03, 3.97. They are not the same. They are not opposites. Okay? I would say most people would have bet on even for that instead of being careful there. The proof, obviously, the algebraic proof does show me also that it's neither. Other homework questions? Did we do 31 by any chance or not? We did not do 31, but we did something similar. That has a flat part in the middle. So that was an interesting one. Any other homework questions on 1, 2? Really? Okay.
Could you go over 24?
24, yep. We didn't do 24. We did 22. 24 is, I mean, those are good ones to do. Seriously. I know those aren't evens, or those aren't odds, so some of you wouldn't have even glanced at it. Okay. Is there a point of discontinuity at x equals 0? G of x equals x over x minus 2. Obviously, we're paying attention to the denominator. Is there a point of discontinuity at x equals 0? If there's a point of discontinuity at x equals 0, that means if I plug in 0 into this function, the whole function is going to implode. Yes, fall in on itself. Be destroyed. Like one of those big buildings that they're blowing up, but they have to bring it all in on itself, otherwise they kill people. Can I put 0 in that or not? So 0 over 0 minus 2. Do you guys know what that is? That is 0. So ding, 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 it worked. Therefore, it's not a point of discontinuity. Do you know what point of discontinuity exists in that function? Even though 0 is not it? 2, thank you very much. 2 is a big problem. Can you tell me whether it's removable or non-removable? That's a non-removable one, right? Non-removable. There's no factor that you can cancel out there. Don't you try to cancel out those x's. It's a good way to lose a finger.
Couldn't you?
You have one factor of x in the top, and you have one factor of x minus 2 in the bottom. Those are not those are not the same. Okay. Now, if I had another x out here, well then, yeah, that would work. Or if I had another x minus 2 in the numerator, that would work. Okay, I got another one for you that I'm going to make up here. And so everybody needs to write it down somewhere. If I can actually... find some empty space here. Oh yeah. Don't use a graphing calculator. I want you to use your brain. Okay, no graphing no Desmos. Don't you even try it. I see him over there reaching for Desmos. I need you to think about what this looks like. I think you would be better served if you factored the numerator. So do factor the numerator right now. Go. Come on. Factor that numerator. If you don't factor the numerator, you're probably going to stare at it for a while. Yeah, write that one down somewhere because it's not one of those problems. I just made it up. Just made it up.
It'd be 0.
Okay, now draw the picture. Without a graphing calculator, draw the picture. Yes, almost. After you factor the numerator, look for something that cancels. Find something that cancels. Okay. After you cancel out the factor that does cancel, graph the doggone thing. Because I'm sure everybody in the room should be able to graph this. All right, so what did you do for factoring the numerator? You took an x out, right? Okay, some people think that's weird. But, you know, if you get along with your x, that's fine. Okay, so if you pull out the x, then what did you do? Canceled out the x minus 10s, hopefully. What are you dealing with here? What is this equation you're dealing with? Y equals x. Now, every one of you should be able to graph that right now very quickly. All right, you got your picture already drawn? All right, let's see if we agree. Hopefully you drew a line. Hopefully your line goes through the origin. Hopefully your line has a slope of 1. And hopefully that cool line also has a hole in it. Did you draw the hole? No, you forgot to draw the hole. Now, where do you think that hole exists? Ah, when the x value is 10. And so what kind of point of discontinuity is this? Removable. Every one of you knows how to graph y equals x. But the whole idea of this extra factor in there causes that removable discontinuity. I'm sure when you guys stare at that original function, you're like, what the heck is that? But with a little bit of algebra, it gets to something manageable. It's whether or not you realize what that removable factor does to the graph. So tomorrow we're going to dive into 1-3. Yes, I will make sure you have done your 1-2 homework. But we're going to start with 1-3. It will go, 1-3 will go a lot faster now that we spent 7 days on section 1-2. That's the longest you'll ever spend on any section in this entire book. It's a big, important section.
Are we only